Okay, hello everyone. So today we are going to start our new topic, which is about handling interrupts. Last time we have completed our discussion about timers, timers 0, 1, and 2 in NetMega 3 to 8P, and how we can use them in two different modes, which is normal mode and CTC mode, but we didn't cover the two other modes which are available, pulse wave modulation PWM and the interrupt input capture mode. So today we are starting the discussion about interrupts. Uh, so Actually, there are two ways through mechanisms or two or different approaches through which uh, any external device it can request service from the microcontroller. And when we say service, it means that it can tell the or notify the microcontroller that whatever job I was supposed to do, I am done with that, and now I'm just informing you. So maybe you need to take some action. What is example of this? An example of this we have seen in the discussion about timers. Remember, what we were doing is that we were initializing the timer register with certain values, and when it was operating, for example, in normal mode, so we were waiting for the timer register to overflow. To overflow mean to reach the maximum value and then change down to zero, right? And how we were waiting, we were actually continuously checking the overflow bit in the TIFR0 register, for example, right? And how we were doing that? By continuously checking what is the value of that bit in the TIFR0 register. And if that value is zero, it's mean that overflow has yet not happened. So we will keep looping in that loop. But if the value of that bit is set equal to 1, it's mean that overflow has happened and now we can continue. So this is one approach, and this is known as polling. We are continuously polling or checking a certain bit. And by we, I mean the microcontroller. So when microcontroller is doing that, it is continuously running in the loop. So let's say that microcontroller, let's say that you initialize the register with 0 and it is 8-bit counter. So it counts to 256. Now what will happen? That for 255 times when the microcontroller will check, the flag is not set, right? And on the 256th time, the flag is set. It's mean that in the first 255 times, microcontroller was sitting idle. It was doing nothing, right? It was wasting time. So wasting time in the sense because it was not doing any useful work. It was simply checking again and again the flag, right? So uh, this is polling, and the bad thing about the polling is that yes, by using the polling, for example, our timer can tell, okay, I have reached the overflow point, but then uh, due to polling, the microcontroller cannot do anything else because it is tied down to checking the overflow bit of the register, right? So it's in other words, we are wasting the wasting the microcontroller, right? What is the other option? Here we are comparing the interrupts and polling, but we first need to explain what is a polling and what is the interrupt. So let me simply connect my OneNote, my drawing pad, and then I will go to OneNote to explain in a bit more detail. Okay. Yeah. So I was giving you example of polling in context of timer, right? So and we have seen those examples multiple time in our previous lecture slides, right? So uh, so what we were doing was like uh, suppose this is your TIFR0 register, and this is the bit at the 0th index, which is basically your timer 0, overflow flag for timer 0, right? So what after putting the value in TCNT0 register, what you were doing, putting anything, well, let's say putting the value 0, right? And then what we were doing in our code, what microcontroller was doing, I'm not writing the code, I'm simply trying to like show it using some drawing. So it will start checking the this flag, right? So on every upcoming clock, the value of then this TCNT0 register is incremented. So it checked when the value is 0, no overflow flag. Overflow flag is not set. Then value is incremented to 1. Is the overflow flag set? No. At 2, is the value of overflow flag is set or not? No. And we continue, right? Finally, when we reach 255 and down the next clock, when it is changed from 255 to 0, then this flag is set, right? It means that for 255 times microcontroller, when checked the flag, it found that the flag is not set. And on the 256th time, it found that flag is set. But and then it can continue with the rest of the program, right? But what is the important observation here is that microcontroller is tied for 255 cycles, can't do anything else because it is continuously checking or polling the overflow flag, right? So yes, we are able to detect if an event has happened. For example, the flag is set, but this polling approach is not good in terms of using the resources. So what is the opposite of that? So for example, what I want to do is the following, that I am doing some task, like for example, my microcontroller is continuously sending the data from port C to port D. I'm not writing code. I'm just trying to explain, right? You can write the code to perform this operation, right? Continuously read the data from port C and send it to the port D, right? So I want my microcontroller continuously doing this, right? But before I started doing this, like continuously read, before I entered it in this loop, I set the timer. I initialized the register with value of 0 and I started the timer. And now I started doing this, right? But what I want is also that when this flag is set, when the overflow has happened here, I want to immediately go to a program which performs some action mean, like for example, if this flag is set, then generate an output, scare output on the let's say PB5 pin, right? So if I was using polling to check if the flag was set or not, I cannot do writing, copying data from port C and sending it to the port D. I can't do these two things at the same time, because either my microcontroller can continuously run in a loop to check the flag, or it can do this second task. So I'm just simply naming them as task 1 and task 2. So when I'm doing polling, I can't do these two tasks at the same time. However, there is another mechanism of giving service, providing service to the external devices, or taking care of events, which is known as interrupt. So in interrupt, what we do is that our microcontroller don't need to poll this flag continuously. You can simply start the timer, and then you can start copying the data from port C and sending it to the port D. And then when the value of the timer reaches from 255 to 0 and the flag is set, then automatically you just need to provide a program, right? And then automatically what will happen, that microcontroller, let's say it was in middle of here, it will stop and it will start executing this program, which will take responsibility of generating this scare waveform on the output PB5 every time when this flag is set equal to 1, right? And then it can come back and start executing exactly at the same point where it was before, at the time point when the flag was set. So the main difference between polling and interrupt is that polling wastes the resources because your microcontroller can't do anything else because it continuously polling and checking the flag. But the interrupt allows you to continue doing something else, and once the event happens, for example, in this case, the setting of the overflow flag of the timer 0. So once that event happens, microcontroller will automatically jump to a location where you have already stored a program, and then it will execute that program. And then that program will do whatever it is supposed to do. For example, in this case, we have placed a program here in the location which is responsible for generating a scare wave on the pin PB5. Okay. So any questions here before I go ahead? Any question regarding if you don't understand what is the main difference between polling and interrupt-based handling of events? Okay. So assume that let's say we want to develop an application, microcontroller based application, which actually take care of like if there is fire in the something is on the fire, then our application or our project need to take care of it by taking some action, right? And for example, for that to sense the fire, let's say we have connected a sensor with an input pin at like which is the pin D.2, right, of the microcontroller. So if there is if we get the signal that there is a fire, our sensor tells us, then we need to deal with the fire. Otherwise, we need to do something, right? So, but in the polling, what we will do is like we will need to continuously check we will need to continuously check the pin D.2, right? Because here we are running in the loop. Here we will be running in the loop and we can't do anything else, right? So for example, if consider the worst situation where there is no fire and our sensor never gives us any signal, then we will not be able to do anything else. We will simply forever checking the sensor value all the time, right? And microcontroller will not be able to do anything else, right? So yes, but in the case when fire happens and the sensor gives us a signal, then we will be able to detect it. But in the case when the sensor gives us no signal and because there is no fire, then we are wasting our microcontroller, right? So the good thing about this approach is that we don't need any special hardware, any special component or an additional component, right? If we, as long as our microcontroller supports the capability or feature to read an external input, we are fine. We can use the polling and we can use the polling to detect the events, right? The disadvantage is that it ties down the CPU or it occupies the CPU all the time, and sometimes this can be also very slow. As compared to the polling, now we have interrupt. So here what we do is like, let's say you are doing some main task, right? And then you have an interrupt handler, which actually in the previous, which on the one note I showed you as a code, right? So interrupt handler is nothing but a code. So when an interrupt will, like for example, when the fire will be detected, then the code which is responsible for taking action, that code will be run. And we are simply naming it as interrupt handler, okay? And this interrupt handler will be called automatically by your hardware or by the microcontroller whenever it detects the signal. So you don't need to continuously poll the pin, to continuously monitor the pin D.2 to find if there is fire detected and then go ahead and run the code, right? So what you can do is that microcontroller can do some main task, some common task, and while it is in middle of doing that, if it detects that there is a signal on the pin D.2, it will automatically go to the interrupt handler code and execute that code. So which means that now you can do two different things at the same time. So you don't need to, like, you are not occupying two different things in the same time, means like you are not wasting your microcontroller in continuously monitoring the pin. So advantage is that here we are using our CPU more efficiently because we are not wasting it in monitoring the pin or a flag or a bit, right? The other thing is that we can have interrupts with multiple priorities. So it basically means like, uh, let's say if we have three different interrupts and we have written the interrupt handler or code for each one of them, so we don't need to worry about them because each of them have their own priorities. Once we have assigned them priorities, after that, it doesn't matter. It is not our responsibility. So for example, if let's say interrupt 1, 2, and 3, all of them happen at the same time, then since we have already assigned them the priority, microcontroller will run the ISR, or sorry, not let me not use the word ISR. The microcontroller will execute the interrupt handler of the interrupt which has the highest priority automatically. We don't need to worry about that, right? However, if we are using the polling, we cannot handle multiple events, and we can handle multiple events, but in like a round robin fashion, which basically mean one after the other. So if we are processing them or handling them one after the other, first let's say I check flag of timer 0, and then I check, and then I take some action, and after that I check the flag of timer 1, and then I take some action, and after that I check flag of timer 2, and then I take the corresponding action. So it's mean like I am checking them one by one, right? Like in turn. So it's mean that I cannot assign them priorities because I am checking them in one by one. So like first, if I'm saying that the sequence is first check the flag of timer 0, then 1, then 2. So all of them must wait for the other two to be completed, right? And then they get their turn. So there is no priority involved. So that is problem with the polling. So with the polling, yes, you can monitor the multiple flags or multiple events, but you cannot assign them priority. However, you can assign priority when you are handling events using interrupts. And also it is efficient in multitasking. Multitasking means that you are doing some common task, and when the interrupt happens, so you are doing the common task, so you don't need to continuously monitor the flag. When the interrupt will happen, microcontrol will automatically jump to the place where you have the code for handling that interrupt, and it will execute that code. However, the bad thing is that in order to support the interrupt-based handling of events, you need to include special CPU hardware in your design, right? So, for example, in your microcontroller, at Mega Microcontroller, you have an extra unit which is named as interrupt unit, which is responsible for taking care of interrupts. So, but if you, let's say you say I don't want to support interrupt based handling of the events in my microcontroller, then you don't need this unit. Then you can simply, by using other instructions, until as this point we have done this without using any interrupt related registers, we are able to handle events. So you can use the polling, right? But then, as I said, polling is not efficient. It wastes your resources or wastes your microcontroller time. Okay, so remember in one of the previous lectures, we talked about status register, right? And we discussed other flags in this register, which was like, for example, carry, Z flag, negative flag, overflow flag, sign flag, half carry flag, and T, I don't remember what it was, but we have covered all these flags. However, not the T flag, I guess we didn't discuss it. But we also didn't discuss the I flag, which is interrupt flag. So this flag is basically used. So here is the thing. There, if you want to enable the interrupts, so there are two levels of or two steps for enabling the interrupt. First thing is like there are many different kind of interrupts, right? And each of those interrupts have their own bits to enable or disable them. However, we have one global flag, which by setting it to 0 or 1, you can disable or enable all the flags, all the interrupts in your system. So this is the flag for enabling or disabling the all the interrupts in your microcontroller. So how you can set this flag equal to 0 or equal to 1. So to set equal to 1, you can say, okay, set interrupt. You can execute this instruction SCI, which will actually write a value of 1 in this bit of the status register. And when you execute the instruction clear interrupt, so it will write value of 0 in this bit of the status register. So if you write 0, all the interrupts in the system, they will be disabled. And if you write 1, then you are enabling this global register, but then at the same time you will also have to enable the for example timer specific flags, which are timer specific for enabling the timer specific interrupts. Okay, we will see an example and then it will become clear. Any questions at this point? Okay, so remember when we were talking about writing assembly language code about for implementing the functions and how to call the functions, we said that we need to follow some certain steps, right? So what were those steps? So before calling a function, we first need to save any of the registers which we expect that they can be modified by the Kali function. So what we do is that we were pushing them to the stack, and then after that we call the function, and then the body of the function which we call is executed. And then once it is executed, what happens at the end, we were putting the return instruction. What was the job of the return instruction? Sorry, when you do the call, the instruction of the okay. Uh, Again, let me go back to the one note. So let's say you have a assembly program, and here you are saying call foo, and after that here you have instruction X, right? So what will happen when you say call foo? So your at this time PC is pointing here, next instruction. So the address of this next instruction, whatever the value of PC is, it will be pushed on the stack, right? So let's say our top of stack is this one. So PC will be copied here. And then the control will jump to the code where we have label foo in our exam in our code, right? So for example here, if you have instruction 1, so this instruction will be executed, then next one, and then finally at the end you have return instruction. So what was the job of the return instruction? It will actually get the value from the top of the stack and put it in the program counter. So this value will be copied back into the program counter register, and then now big program counter is actually pointing to this instruction here. So the next instruction that will be executed is one, which is after the call instruction, right? So this was the, like, there was a sequence of the steps in how you actually perform the function calling in assembly, right? So similarly, there are steps in executing an interrupt. So what are those steps? The first thing is that the microcontroller. So again, so let's say we again follow the same example of timer 0, right? What we did is that, let's say we enabled, we will talk about how to enable the interrupts, but let's say we have already enabled that interrupt for the timer 0, which basically we are saying, like, when its value, when the overflow happen, then we need to do, so this is, let's say, overflow flag, right? So when the value, this value of this flag is set equal to 1, then we want to do something, right? And when we say when we want to do something, it's basically means that we want to execute the interrupt handler, right? Which for the time being, I'm simply naming it as a code, because if I use some other terminology, then you will be confused, right? So what we want to do is that once this flag is set, we want our microcontroller to execute this code, right? However, Currently, our microcontroller is running this code, which I'm naming as let's say main code, right? So there are instructions which are being executed. Now just assume that microcontroller is executing these instructions in sequence, one after the other. And currently, let's say we are at this instruction X, right? And while we are at this instruction X, remember, we have already initialized our timer and we have enabled it and it was counting, and the overflow happens when the microcontroller was executing the X instruction X. Now what will happen? The microcontroller will complete the current instruction. It will complete this current instruction before it will respond to the interrupt, right? Before it will take care of the fact that an event has happened, and that event is the setting of overflow flag of the timer in our example, right? Then what it will do is that it will save the address of the next instruction. What is the next instruction? Let's say it is instruction Y, right? So it will say the address of the next instruction, which is available in PC on the stack, right? So let's say this is our stack, and here we have top of stack. So PC will be placed at top of the stack, right? Then it will jump to a fixed memory location called the interrupt vector table. So don't worry for the interrupt vector table name for the time being, but just this third step only means that after putting the value of the program counter on the stack, on the top of the stack, the microcontroller will go to a known memory location where you have the code written to take care of or to do something. Overflow happened for the timer zero flag in our case in this particular example, and which basically mean that this code will be start executing, right? uh, and this code is actually since this code is responsible for taking care of the interrupt, and by the interrupt here we mean that the overflow has happened, so that's why it is named as interrupt service routine, because it is this code is responsible to service the routine, to service the interrupt. So that's why we are naming it as interrupt service routine, and it will start executing this code. But however, before executing the code, microcontroller will do one thing more. It will actually disable the global interrupt. How? By actually, where is that register? By setting this bit equal to 0. You don't need to add any extra instruction. Hardware knows on its own that when an interrupt happens and it is supposed to execute the interrupt service routine, so it will, before executing the interrupt service routine, it will set this bit equal to 0 on its own automatically. You don't need to worry about that. Okay. And then it will execute the ISR, which basically means this code here, right? And until it reaches the final instruction. Remember that whenever we have a code responsible for taking care of an interrupt, which we are naming as interrupt service routine, the last instruction is always return I, RETI. Just like always an instruction, a last instruction in the body of a function is return. Similarly, the last instruction in the body of an ISR is return I. So it will execute all this instruction until it finally reaches the return I instruction. And at that point, what happens? It will restore the saved PC. So remember, we stored the value of PC here. Now the microcontroller will read that value and put it in the PC register, right? But also it will do something else too, and that is enabling the global interrupt. Remember, when it started executing the code of ISR, it disabled the global interrupts by putting 0 here. Now it will put 1 back here to enable the interrupts, right? Why it was disabling before starting the execution of ISR? To make sure that when it is serving the current interrupt, no other interrupt arrives, or if even if it has arrived, it will not be taken care of. So these are the steps. Yeah, so the global interrupt will be enabled again. And since we have restored the PC, now the next instruction that will be executed will be this instruction Y in the main program sequence. Okay. One thing, okay, let me just delete these annotations or drawing. So one thing which we need to be very careful about ISRs or interrupt service routine is that if within the body of interrupt service routine we want to use stack, for example, for pushing some data, so we must make sure that there are equal number of push and pop, right? Which basically mean that whenever you are pushing some data within the ISR, if you are pushing something on the stack, before leaving the ISR, you must pop it off the stack. Okay. Otherwise, you will not be able to return back to the main function, return back to the point where the interrupt happened. Any questions at this point? So if you are equal, there are not equal number of push and pop instructions, so your stack handling will be improper, and as a result, you will not have the correct return address. Okay, so interrupt service routine. So remember in the last slide, I used this word interrupt service routine, and we said like basically it is nothing but the code which is responsible to take some action when an interrupt happens, right? So it is a program that is executed by the microcontroller when an interrupt occurs. However, there is one ISR for each type of interrupt. Remember, there is not like there are many different type of interrupts which are supported by the microcontroller, and when any one of them happen, it must have its own ISR, and its own or its corresponding ISR is then executed by the microcontroller. So every interrupt has its own code for handling it or its own ISR. So there are fixed locations in the program memory where ISR for each type of interrupt must be loaded or must be written, right? So when the interrupt happens, microcontroller will start executing automatically from memory location allocated for the corresponding ISRs. Let me explain here what I mean, right? So for example, remember, so what is this table? So this table is actually giving you the info. This is known as ISR. Sorry, it should be named as ISR interrupt vector table, not IS. Let me correct it. So this is your ISR interrupt vector table, and what does it? What is the significance of this table? So here it tells us like on in the first column you have vector number, in the second you have memory addresses. These are memory addresses. Okay. Third column actually tells you the type of interrupt. Uh, Type of the interrupt, and the fourth is like just a definition or brief description. Now let's take a particular example which we are familiar with, right? We have covered timer in previous lecture, right? And we have covered timer 0, timer counter 0, and we know that it has an overflow flag, right? Now we know how our flow flag is set when the value of the timer counter register changes from 255 to 0, right? So previously what we were doing was we were just continuously monitoring that flag, and then once it is set, we were uh, toggling the output every time to generate a scare wave, right? This time what we want to do is that let's say we want to again do exactly the same thing, generate the scare wave on the output by toggling the output every time the overflow happens, but we don't want to monitor the flag continuously. We want to use interrupts for that purpose, right? So it means that what we want to do is that whenever an interrupt happens, which basically means whenever the overflow flow happens, we want our microcontroller to run the code which toggles the output toggles the output. If it was 1, then it makes it 0, and again next time when the overflow will happen, it makes it 1 again, and next time when overflow happen, it makes it 0, and so on. So we will have like a scare wave on the output then, right? But we don't want, again I'm saying it again, we don't want to monitor the overflow flag continuously, which means we don't want to use the polling which we were doing in the last week, for example. Okay. So it's mean that we need to write this code. Okay, it's fine. We know how to write the code, let's say. But the requirement is that this code must be stored in the memory at the location 0x0020. So our first instruction of this code, it must be stored in this address, right? So, so here we are naming this code as ISR. So what we are in a technical term, and what we are saying is that ISR of timer counter zero overflow, ISR of this interrupt must be stored at this location in the memory 0x0020. Okay. So when timer zero overflow interrupt happens, so then microcontroller, what the microcontroller will do, it will start executing at address 0x0020. So this time we are not polling. As soon as the overflow flag is set equal to 1, microcontroller will automatically jump to this location and will start executing instructions from this location, right? Now, if we have stored our code responsible for generating the scare wave at this particular address, then that code will be run and our scare output will be generated, right? However, However, if you see here carefully, we are given only 2 bytes to store this code. Only 2 bytes of the memory to store this code, because we are given the address 0x0020 and we have then 221, but we cannot use 22. Why? Because 22 is used to store the ISR of another interrupt, which is SPISTC, right? The type of interrupt. So it's mean, how can we write a code which is only 2 byte long to generate a scare wave? It is not possible, right? So then what we do is that in this address, let me just draw here. So let's say this is your memory and this is the address 0x 20, right? I'm not writing leading 2 zeros. So I cannot write here a complete code for generating the scare wave. So because I have only 2 bytes available, 20 and 21. So what I can do is that I can put a jump instruction in this. So we can place an instruction that jumps to another address holding ISR. So for example, I actually have written the example here. So this here you are saying go to 0x0020 and put there the instruction jump to a label, right? So we are simply putting here this instruction jump, right? So when your overflow will happen, when the interrupt arises, microcontroller will automatically go to this location. It will see, okay, there is jump instruction. It will execute the jump instruction, and jump instruction is then saying, okay, go to the label timer zero overflow ISR. And then here you have the code of that code which is responsible for generating the scare output, right? You execute it, and the last instruction of an ISR is always a return interrupt instruction. Okay. Any questions? No? Okay. So there are many other types of interrupts in the at Mega 328P, but we cannot discuss them, all of them in this course. One thing. Second, maybe in the next lecture we will cover some other interrupts not related to timers, but let's start first with the interrupts related to timers. Why? Because we have covered the timers in the previous week. Now we have the knowledge and we can now build on top of that knowledge to handle the interrupts, right? So the principles or the concepts are same. They can also be applied on other type of interrupts, but if, for example, if you want to use the interrupts related to serial communication, you first need to understand how serial communication works, right? In AVR microcontroller, and then you can use the interrupts related to that serial communication. But we haven't yet covered it, so it doesn't make sense to first cover interrupts of other components. So we are just skipping them at this point, and we are going to cover the timer related interrupts, right? Now, There are three registers in at Mega 3 to 8P. Again, there is a disclaimer. So if you are like reading the textbook, so in the textbook they have chapter 10 about interrupts. So, but they discuss the interrupts in context of microcontroller at Mega 3 to 8, not 3 to 8P. Now, at the microcontroller 3 to 8 and 3 to 8P, they are different from each other in their capabilities, right? For example, in 3 to 8P, they have a single register, TIMSK. They don't have three separate registers for three timer 0, timer 1, and timer 2. Okay. So if you are reading the book, so don't get confused because in the course we are using and in the lab we are using at Mega 3 to 8P. That's why in the lecture slides I wanted to focus on the registers related to at Mega 3 to 8P, because let's say if in the next lab we are working with the timers and uh, our slides are based on the book, so then there will be difference in registers, and then there will be also register a difference in the vector table. So for example, the addresses which are used for timer 0 overflow interrupt in the ATmega 3 to 8 microcontroller is different than the address used in ATmega 3 to 8P. Okay. Okay. So having said that, now we have three registers, timer interrupt mask 0, timer interrupt mask 1, and timer interrupt mask 2. Now, as clear from their name, they are related with timer 0, timer 1, and timer 2, right? And let's start with timer 0. So all of these three registers are 8-bit. So if we start with timer 0 and look at its timer interrupt mask 0 register, so only 3 bits are used: bit 0, bit 1, and bit 2. So bit 0, it is used to enable the interrupt timer overflow interrupt for timer 0. So we are in, if we write 1 here, then whenever your timer has an overflow, then an interrupt will happen, right? But if you write 0, then if it is equal to 0, then interrupt is disabled, which means like even if there is an overflow from 255 to 0, your microcontroller will not detect an interrupt. Why? Because you have disabled the interrupt here, right? So it's mean that if you have written here 0, you can use only polling to take care of that overflow event if you want to take care of it. However, if you want to use interrupt based handling of that event, so first you need to write 1 in this bit. Okay. Similarly, remember that timer 0 can also be used in CTC mode. What we were doing in CTC mode, we were putting some value in output compare register, right? And when our timer value was time value of the timer register was becoming equal to output compare register, a flag was set, output compare flag, right? For output compare flag for both comparator A and comparator B, there were two different flags, right? So what we can do is, again, if you want to use polling, then by default, all of these bits are 0, right? So you can use only polling to where you continuously check the flag, as we have done in the examples in the previous lecture, right? But if you don't want to use polling and you want to use interrupt in the CTC mode, so then you need to enable these interrupts by writing 1 in the corresponding bits. So if you write 1 in OCIE0A bit, it's mean you are saying that when the value of the output compare register A becomes equal to the timer register's value for timer 0, then generate an interrupt, and which mean that microcontroller will then, as soon as those values become equal, microcontroller will jump to a location, particular location. And which location? You can actually check it from here, this one here. So it will go to the memory location 0x001C, and whatever code is written there, or let's say you have not written any code, it contains garbage, it will start executing garbage. Okay. So it's mean that if you are enabling the interrupt, you also must write an ISR. Otherwise, if the interrupt happens, and there is you have not placed any valid code, there is garbage, your microcontroller will start executing garbage. Okay, so in the same way, you also have timer interrupt mask 2 register, which the functionality of these bits are exactly same, but only for the timer 2. And then you have also timer interrupt mask 1 register. Again, the meaning of these bits are exactly same as for timer 0 and timer 1. Then it has an extra flag, which is actually for input capture interrupt enable. Since we haven't covered the timers in this mode, like input capture mode, we are not going to talk about this type of interrupt here. Okay, so like if we focus only on these bits, so they actually provide 9 different type of interrupts, right? And that's why you will see here you have like 9 different entries covering in the table, covering all of those interrupt types, actually also including the capture event. So if you count it, then it will be like 10th. Any questions? So to enable the interrupt, you need to write 1, and to disable, you need to interrupt. You need to write 0. Okay, now let's have a look at an example. Suppose that we want to use timer 0, uh, but we want to use its overflow, but in interrupt mode, right? Which means that whenever the timer 0 overflows, we want an interrupt to happen, and then we write the ISR to take care of that interrupt. Okay, so use timer 0 to generate a scare wave of period 8 microsecond on pin port B 8.5 at 8 megahertz clock frequency, and while data is being transferred from port C to port D. So let me just first clarify the problem statement to you, and I'll try to make it visual, and then we can look at the A Victor V2 H2. Okay, so this is our problem statement, right? So what we want to do is this. Let me draw it. So you have port C, right? Let's say you have connected 8 switches with port C, 8 switches. I guess at Mega 328P, we don't have 8, but we have 6 pins. Let's say we have connected 6 pins, 6 switches, and we are using port C as input, and then we are using port D as output. And let's say it has LEDs. So what we want to do is that continuously connect, read the value of the switches and put them on the LEDs, right? But that is not all what we want to do. We want to do something extra, which is at pin port B.5, we want to generate a scare wave, right? And the period of this scare wave is, oh, sorry, until this point, it is 8 microsecond, which means that it should stay high for 4 microsecond and then stay low for next 4 microsecond and then so on, right? So, but we want to do these two things at the same time. Like we continuously read from port C to port D, and then we are also continuously generating the scare wave on the port B.5. And for that, we can do this only by using timer in the uh, timer interrupts. If we use polling with the timers, we can't do that, right? Okay. Is everyone clear about the problem statement? Any confusion before we go to have a look at the code? Okay. So silence means that there is no ambiguity, right? So, okay. Uh, so first thing, here we are in our program, we are putting this directive org0x0. Anyone who doesn't know what this directive is doing? Does everyone know? Is it clear what is this directive is going doing? Okay, so it will tell our assembler to put the any instruction which we write after this directive at the address 0 in the memory location. Okay, so again, uh, maybe I can keep them both side by side. Yeah, so here what we are saying is in the first in this statement, so we are saying that go to the memory. Let's say you have, this is your memory, right? And you are saying, okay, in the memory at location 0, put the address jump main, put the instruction jump main, right? And what is main? Main is your label here, right? Now, why we are doing that? Why? Because if you look here in this vector table, we have an interrupt which is known as reset, right? And the address for the ISR of that interrupt is 0. So which means that whenever the microcontroller is reset, the first instruction that is executed is the one that is stored at the address 0, right? Which means, right, when you are on your Arduino board, you push the reset button. So it executes the first instruction. The first instruction that is executed is the one which is stored at address 0, right? Now, that's why we are putting jump main in the address 0, so that when this instruction is executed on reset, the control immediately transfers to our main program here, right? We are saying jump main and then it will start executing from this point. Okay. The next thing we are saying in our code is that at address 0x0020, put the instruction which says jump and then it gives a label. The label is timer 0 overflow ISR. Now, why we are selecting this address? Because we want to use our timer. What we want to do is that whenever there is an overflow interrupt for timer 0, we want its ISR to be executed, right? Which means that we must put its ISR at address 0x0020, which you can check from the table here, right? This address, right? But again, as I said earlier, we have only 2 bytes, 20 and 21. So we cannot put the whole code of the ISR there. So we are saying, okay, jump to this label. And then we have defined the label here. And this is the code of the ISR. Note that the last instruction here is return interrupt. I will explain what this ISR is doing, but for the time being, let's try to understand the code in sequence. Okay. So now, if again you just want to visualize, so it will look like something like this. That here at address 0x00, what was the address? 0x0020, you have placed the instruction jump and then label, which is timer 0 overflow ISR. Okay. Okay. Then you are saying, okay, at address 0x10, at address 0x10, put the this remaining code like now uh, again, if I want to visualize, so at address, let's say 0x100, you will have the first instruction which says load immediate R20, blah, 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 blah. Okay. So, okay, now what we are doing in the main code now. So here we are saying, first we are initializing the stack, and we have done it so many times in previous examples, so I'm not going to explain it. You are simply saying, okay, put the value of high 8 of the RAM and in the stack pointer high register, and put the value of low 8 bits of the RAM and in the stack pointer low register. Okay. After that, remember we wanted to use port B.5 as output. So we are making it, configuring it in the output mode by saying, okay, set the bit at index 5 of DDR-B register, right? And then we are going to make these ports, configure these ports. So we are first configuring the port C. Yeah, first we are configuring the port C in the output mode. We are putting 0 in R20 and sending R22 direction register C. So now we are done with C. It is now configured as input port, and then we are putting all ones in R20 and sending it to DDR-D. Now port D is configured as output port. Okay. Now we are done with that. The next thing we are going to do is we need to enable the interrupt, right? We need to enable the interrupt of what? We need to enable the overflow interrupt of timer 0, right? Now, if you remember from the last lecture, and if you don't remember, I can tell you that uh, okay, we don't need the last lecture at this point. So TOIE0 is the bit at address at the index 0 of TMISK0 register. We need to set this bit equal to 1, right? To enable. So what we are going to do here is we are saying simply shift 1 towards left. How many time? TOIE0 time. Actually, it is not defined here, but you can here put just simply a directive which says equate, I don't want to write, equate TOIE0 equal to 1. So equal to 0. So now you are actually putting 1 in R20, and then you are saying, okay, now write R22 TMSK0. So which means that in this register TIMSK0, all the bits will be 0 other than the bit at index 0, right? So this bit is set equal to 1 and all other bits are 0. But this is not enough, right? This is not enough for enabling the interrupt. Remember, there are two levels for enabling, or two stages are enabling the interrupt. First, you enable the interrupt in which you are interested. For example, in this case, the overflow interrupt of timer 0, which we have already now enabled by writing 1. And then you also need to enable the global interrupt in the SREG register, if you remember. This one, you need to write here 1. Remember, all the interrupt bits, interrupt enable bits or interrupt enable flags, all of them are 0 by default. Okay, so when you reset your microcontroller, here you have 0 by default. So you need to enable it. Okay. So we are going to do that in the next instruction. So here we are saying enable the global interrupt flag in the SREG register, status register. We have 5 minutes, so I hopefully I will be able to complete it. If not, we can do it start from the same point in the next lecture. So here we are done with enabling the interrupt. Now what we are going to do next is that in the timer counter register, we are putting the value of we are going to put the value of -32. Why? Because it corresponds to generating a delay of 4 microsecond. How? I'm not going to do it again. You can simply go to the previous lectures and see, like, for example, if you want to generate a delay of 4 microsecond, what value should we put in the TC and T0 register, and you can calculate that value and you will end up having -32. So we are putting in -32 in TC and T0 register, right? And then uh, we need to write the register, control register A and B. Actually, there is a mistake in this example, in the sense that this example is written for at mega 328, not for 328p. So let me stop here because I don't want to confuse you. So we can start again from exactly same point next time, because I need to fix this example and adopt it for at mega 328p, where we are writing timer control registers A and B, both registers. And then it will be, this example will work for at mega 328p. So let's stop here. Do you have any questions uh, before you go for the quiz? No? Okay, if no questions, then I am here. You can take this. Let me stop recording. Yeah.